And hello, we'll be presenting our assignment 2 for algo analysis. So there's question 1 and 3 for implementation. So we'll start with question 1. So as you can see here, there's a user interface, and I execute question 1 using 1 here. And you can see all the available images for us to select. So these images arrive from here. So our solutions directory, if you go to the images folder, you can see all the images here. So they will be run here. So we will choose an image. So for now, let's choose download.png for this case. We gave the options to check the energy map if you want to see it. So we would say yes. Then let's remove about 250 seams from this image, both for vertical and horizontal. So I'll pass it to Austin, who will explain the process.
Thank you, Ryan. Hi, I'm Austin, and yeah, I'll be showing a short demonstration of our seam carving. So once I hit enter, firstly you can see the energy image window, and followed by this original image window. And at the top left, you can see a seam visualization which is done real time. And after this is done, you can So this window overall it will be showing overall all the seams that were being carved out during the algorithm. And this final window will be showing the final image after it's being carved. Yeah, and let me try with another image, for example. So let's say I want to try castle. I want to remove, or let's say no, I don't want to see the energy map, and I want to remove 100 vertical seams and maybe 20 horizontal seams, for example. Yep. So let it do its own thing. Yep. And as you can see, the final image is um like being carved out from the original image. Yep. And if I go back to the resize folder, you can see the two resized images. Yep. And so I'll pass the time to wait. Let me. Yep. So I'll pass the time to Owen and Tristan.
Hello, Hi, I'm Owen. Okay, so for our greedy algorithm, the interface is exactly the same, except we have one extra option because we have two different greedy algorithms. The first greedy algorithm does it by seams, and the second does it by pixels, just to illustrate how important it is to follow seams. Because the brief, I think, was not very clear, so we did it by pixels and by seams as well. Okay, so moving on to the question, we're going to do shopper. Okay, I want to see the energy map. I'll do 300 by 300. And then in this case, we are going to do the compression by seams. So I'm going to click no, I do not want by pixels. And this is what the compression is going to look like. Now, because it's a very big image, regardless of how good the algorithm is, it's still going to compress it in a bit of a weird manner. But later we'll show you the algorithm does by pixels, and you can see that it's a big improvement over it. So I'll pass my time to Tristan to show you the pixels.
So hello, I'm Tristan. I'm going to be talking about the greedy algorithm version that cuts by pixels rather than seams. So we just want to illustrate how important it is to cut by a full seam rather than pixels. So if we follow the same image as Owen, so we compress by pixels. You can see because it's compressing by pixels and not contiguous seams, the image gets increasingly distorted, even more so than the seams version. It pretty much doesn't really resemble the original image anymore. So this to show that the greedy algorithm sometimes can be a bit unoptimized. So this in its like rawest form, I would say. So now I'll pass the time to Wen and Yuki to do some analysis.
Hi, so I'm Yuki. I'll be answering question 4A. So the first part is calculating the energy map. The energy map calculated using the Sobel filter processes all m times n pixels in O of m times n. So the next part is to find the minimum seams. So for vertical seams, calculating the cumulative energy across rows takes O of m times n. And similarly for horizontal seams, it also takes O of m times n. For removing seams, removing a vertical seam takes O of m, and removing a horizontal seam takes O of n. For Ka vertical and Kb horizontal seams, this step has a total complexity of O of Ka times m plus Kb times n. So for repeating the process, recalculating the energy map and finding seams dominate the time complexity. So repeating these steps Ka plus Kb times results in O of bracket Ka plus Kb bracket times m times n. So we also have a visualization toggle for seeing the seams. So enabling this visualization doubles the complexity to O of 2 times Ka plus Kb bracket times m times n. So the space complexity is storing the energy map and cumulative energy table. It requires O of m times n with backtracking for the seam path adding O of m. Thus, the total space complexity is O of m times n. Dynamic programming ensures high quality seams, but it is more computationally expensive. So on to Wen's part.
Okay, this is Wen. So for my part, I'll be comparing with a greedy algorithm. So upon comparison, we found out that the greedy algorithm is actually faster than dynamic programming. Its time complexity is O bracket Ka times m plus Kb plus times n. While dynamic programming is O bracket Ka plus Kb entire thing times n times n. In terms of space, the greedy algorithm only stores the current seam path, requiring O bracket n for vertical seams or O bracket n for horizontal seams, compared to O bracket m times n for dynamic programming. However, dynamic programming produces a higher quality seams by considering the entire image, whereas the greedy algorithm, which is localized decisions, may introduce distortions. Thus, the greedy algorithm is faster and lighter, but dynamic programming ensures better visual quality. So for part C, which is on improvements, we found some issues pertaining to the dynamic programming, which is a large space complexity and hence higher computational cost and the slower time complexity. So for the improvements, the dynamic programming high space and time cost can be reduced. For space, storing only the current and previous rows or columns reduces complexity from O bracket m times n to O bracket n for vertical seams and O m for horizontal seams. For time, recalculating only affected pixels instead of the entire image reduces the recalculations to O bracket Ka times m plus Kb times n much faster than O bracket Ka plus Kb entire thing bracket times m times n. These optimizations make dynamic programming more efficient while maintaining high quality results. This is the end of our presentation. Thank you.